Welcome to this webinar. In this presentation, we look at some of the features in 5G Advanced, also known as 3GPP NR Release 18. My name is Mark Barberis, and I have been a part of the application engineering group at MathWorks for 15 years. My focus is on our wireless standard products, including 5G, LTE, and wireless LAN. At MathWorks and with prior companies, I have followed the different cellular standards from GSM through 5G, including all flavors of 2G, 3G, and later 4G. We start with an introduction to some of those R18 features, then focus on some of them and how they are enabled in MathWorks 5G Toolbox. First up, we'll spend a lot of our time on MIMO evolution. We will also provide an update of AI/ML items in standardization and related MathWorks capabilities. Finally, we review some of the newest capabilities in MathWorks 5G Toolbox before having a look at Release 19 and beyond, with 6G not too far on the horizon. So let us start with a quick context of where Release 18 fits in 5G evolution and a few select features. 3GPP Release 15 back in 2019 was the first release that included the 5G standard. You can look at the evolution of 5G as two waves of enhancements. The first wave includes releases 15 through 17. The second wave, called 5G Advanced, further extends capabilities and starts with Release 18, published at the end of last year, 2023. Let us recap some of the main extensions in the previous releases of the 5G standard. While Release 15 established the basis for eMBB or Enhanced Mobile Broadband, Release 16 introduced key enhancements for EURLLC or Enhanced Ultra-Reliable Low Latency Communications, as well as new capabilities for positioning and V2X or Vehicle to Everything. Release 17 introduced RedCap or reduced capabilities, enhanced NTN or non-terrestrial network, enabled frequencies in the range of 60 to 71 MHz, and increased the maximum data rate by enabling 1024 QAM on the downlink. Release 18, as we shall see in more detail, brought exciting new MIMO capabilities for both downlink and uplink, dubbed MIMO Evolution. It also further enhances RedCap, NTN, and V2X. 3GPP is currently working on Release 19, which is expected to be finalized within the next year. So let us have a look at some select Release 18 features, including a few linked to MIMO evolution. There are several significant extensions to capabilities, both for channel sounding and axial transmission. For channel sounding, both DMRS or Demodulation reference signals and SRS or sounding reference signals are receiving a massive upgrade, with a doubling of the number of ports supported for both of them, up to 24 and 8 respectively. Increasing the number of ports means that you can get a more accurate estimate of the MIMO channel. At the same time, you can characterize channels with a larger number of antennas. This makes it possible to support uplink transmission with up to 8 layers. Additionally, Release 18 includes the possibility to transmit from multiple panels at the same time. On the downlink, new channel state information reporting modes have been introduced in order to better support coherent joint transmission, which means coherent transmission to one mobile from multiple transmit points that are not necessarily co-located. Finally, part of a major push in standardization, which is expected to continue in Release 19 and beyond, companies are looking at ways to save power. One option introduced in Release 18 is to offer SSB-less cells used for carrier aggregation. Another new feature in Release 18 is the introduction of transmission over 3 MHz of spectrum. This was introduced to support mission-critical applications. The context here is that some legacy systems still rely on GSM and LTE-based communication, and some of these systems make use of spectrum that is narrower than 5 MHz. The availability of 5G would make it possible to decrease the communication latency in addition to upgrading to a newer system in general. Taking the example of the US, some of the communications for electric utilities take place on bands 8 and 26, which include 3 MHz deployments. Similarly, rail communications in Europe is currently using GSM-R, and the migration of that technology to 5G requires sub-5 MHz deployments. If we look at the spectrum of the synchronization signal block, or SSB, we can see that its width is 240 subcarriers, or 3.6 MHz at 15 kHz subcarrier spacing. By taking the transmission bandwidth below 3.6 MHz, there now is a situation where the UE is not receiving a complete SSB. Another way to look at it is that the SSB is punctured at the UE by not having subcarriers 0 through 47 and 192 through 239. Due to coding redundancy, the UE can still recover the SSB, but this is a case that has to be specified. At the same time, a new synchronization raster, twice as dense as the previous one, was introduced in TS 38101. The spacing is 600 kHz instead of 1.2 MHz between possible locations in frequency of the SSB. Two separate enhancements to positioning in Release 18 pertain to sidelink, or V2X, and SRS hopping, respectively. Prior to Release 18, V2X waveforms did not include positioning signals. Separately, frequency hopping on the sounding reference signals was introduced in an effort to reduce and randomize interference between cells. Let us now look in more detail at some of the features under MIMO evolution and how MathWorks 5G Toolbox supports them. We shall look at three topics in particular: extensions to the DMRS or demodulation reference signals, those reference signals that enable channel estimation on the downlink and uplink; extensions to the SRS or sounding reference signals, which enable channel sounding on the uplink in any part of the bandwidth part, even in the absence of uplink data transmission; and new capabilities for uplink data transmission, or PUSCH. The goal here was to provide more orthogonal DMRS both on the downlink and uplink, but the major constraint was to not increase the overhead for DMRS. While this may seem at first like two incompatible goals, Release 18 does provide an extension that hits both targets. The new DMRS, which are present in a new DMRS mode, occupy the same footprint in time and frequency. What gives is that the number of DMRS involved to estimate the channel when the number of orthogonal ports is doubled also doubles. Let us illustrate this with a few pictures on the next two slides. If we look at the cases with the most DMRS ports prior to Release 18, these are the cases with 8 and 12 ports. They require using double symbols, meaning two consecutive resource elements shown in the horizontal direction. Configuration type 1 uses a frequency density of 50%, while configuration type 2 uses 2 in 6 positions, which means a frequency density of 1/3. Focusing on the configuration type 2 case, the elements in green and orange, or yellow, represent 4 resource elements and they can carry 4 orthogonal ports because one of 4 possible cover codes, shown as the 2x2 matrices of plus and minus ones, are used to multiply each DMRS symbol value. Because those cover codes are orthogonal, the receiver can separate those 4 ports by averaging the correlations computed on those 4 resource elements after reapplying the cover code. As a result, in each set of 6 subcarriers, 3 times 4, which is 12 DMRS ports, can be conveyed, providing one channel estimate for each port every 6 subcarriers. Release 18 uses the same concept but introduces larger cover codes, which now are 4x2 matrices of plus and minus 1 or j. So the difference is now that 2 of those squares of 4 resource elements now see 1 cover code. This means that there can be up to 8 different DMRS ports per color, and there are 3 possible positions for those elements within a set of 12 subcarriers. The footprint is the same as before, but in order to separate the 24 orthogonal ports, the receiver must now involve twice as many resource elements, and this means that there are twice fewer channel estimation values in the frequency domain. How can you take advantage of these new DMRSs in MathWorks 5G Toolbox? Once again, we've done the hard work for you. So you can simply enable this new DMRS mode by setting the DMRS enhanced release 18 flag to 1, and then picking any port or port set between 0 and 15 or 0 and 23 for DMRS configuration type 1 and 2, respectively. On the right, you can see an example of DMRS layout in time and frequency for DMRS configuration type 1. As mentioned earlier, the footprint is the same as for pre-release 18 DMRS. The main difference lies in those cover codes applied to DMRS. Let us now have a look at the SRS or sounding reference signal extensions. Release 18 defines a new SRS configuration with 8 antenna ports. Being able to sound the channel from 8 antennas provides support for up to 8-layer transmission on the uplink. One of the main drivers for 8-layer transmission is fixed wireless access, and we will see that in more detail next. Release 18 also offers mitigation for interference with the introduction of COM offset hopping for SRS. We will illustrate those latest enhancements in SRS design on the next few slides. First, how do you access those capabilities? You can simply use 5G Toolbox as before, but you now have access to extended ranges for parameters, such as the number of SRS ports, as well as new parameters to reflect the updates in the standard. Let's see 2 examples. Prior to 5G Advanced, the maximum number of ports N that you could set was 4. This means that even if you had 8 transmit antennas on the UE, you could only sound 4 ports. There was no SRS transmission on 4 of them. Starting with 5G Advanced, you can set the number of SRS ports to 8 and therefore sound all 8 antennas, as we can see on the picture at the bottom. Another new capability in 5G Advanced is setting COM frequency hopping to true. SRS are being transmitted using a COM structure, and this has always been the case. What is new is that this COM structure can now vary over time and space. The pictures here shows the resource elements occupied by the SRS in 4 different slots. You can see that the resource elements occupied by SRS change over time and space, which provides interference mitigation from transmissions from other cells, for example. The last item on the list of MIMO evolution items I want to touch on is uplink transmission on the push or physical uplink shared channel with more than 4 layers. As mentioned earlier, one great application for transmission of more than 4 layers is FWA or fixed wireless access. Why is that? I can think of 2 main reasons. The first one is that the user terminal is likely going to be much larger than a phone, and it can accommodate more antennas. The second reason is the fixed part of fixed wireless access. Because terminals are fixed, the base station can better target them and eliminate interferences on both the uplink and downlink from other fixed users. Now, transmitting 8 layers on the uplink is not as simple as just stating it. It is necessary to define new sets of precoding matrices or codebooks for single and multi-panel configuration. As it turns out, the number of possibilities for uplink precoding had to be greatly extended to accommodate this extension. If you look at the number of precoding tables in the standard before release 18, you'll find a total of 6 of them for various numbers of antenna port and layer combinations, as shown here on the left. In 5G Advanced, another 33 new tables were added, or actually 39 of them when counting auxiliary tables, to cover all possible layer and antenna configurations for up to 8 layers. You can see different types of antenna configurations as reflected in the names of codebooks such as NG1 and 4N1, meaning single panel, 4 vertical by 1 horizontal antenna. Toolbox gives you direct access to all those tables by selecting the codebook type parameter. Here is a list of values it can take and the references to the standard table. And as of release 2024B, you can generate those 8-layer push transmissions not only from the command line, but also directly from the wireless waveform generator app by selecting all the relevant parameters, including the number of layers, as well as the modulation and coding scheme for the second code word, the code word used for layers 5 and beyond. Another very active topic in 3GPP standardization is the role of AI in 5GNR, and this is my next section in this presentation. As of release 18, there were 3 topics accepted as study item by 3GPP, which means that they are being studied with the goal of being upgraded to work item for standardization. Those 3 items are beam management, positioning, and CSI feedback enhancement. As of now, the first 2 items made it into release 19 as work items, which means that 3GPP expects them to become part of release 19. CSI feedback is still a study item in release 19. Although a little more detail is needed here. CSI prediction is a work item as of September 2024, whereas CSI compression is still a release 19 study item. We'll talk a little more about those topics in the next few slides. MathWorks has developed many AI-based examples for wireless applications. Here's the list of 5G examples as of release 2024B. You can see a variety of applications from channel estimation to beam management and positioning, and CSI-based feedback, among others. I want to briefly introduce 2 of these examples. The first one is about positioning. In line-of-sight scenarios, positioning based on direction of arrival and/or time difference of arrival works fairly well. But non-line-of-sight scenarios are more challenging. That is the case of a factory floor with many G-node bees and obstacles and reflections on each transmission. The example here compares performance of TDOA-based and AI-based positioning in an industrial setting. This is a case that 3GPP has been looking at in their study. Performance can be compared for line of sight and non-line of sight scenarios. In this second example, we look at channel state information or CSI feedback. CSI feedback is crucial at providing the base station with the information about the channel it needs to optimally schedule UEs and generate beamform transmission towards each one of them. This is a complicated problem, one that trades performance between the simple Type 1 codebook and more complex codebooks with higher performance. For more information about this topic, look for the on-demand webinar called Beamforming for Multi-User MIMO in 5G New Radio. One item that is still being worked on in 3GPP is AI-based feedback, replacing codebooks with AI compression. Here is how it would work. The UE performs channel estimation and possibly pre-processes it to reduce some complexity or make it more easily digestible by AI. Then AI is applied to that information to encode it, and the resulting compressed bit stream sent back to the base station that applies a suitable decoder to retrieve the necessary information. Of course, coordinating the compression and decompression in the UE and the G node B, especially when IP protection is added to the equation, is a difficult topic, and this is keeping a lot of people in 3GPP standardization very busy. What MathWorks offers is a few examples showing how this works. One focuses on the autoencoder by itself, while the other one uses it in the whole context of CSIRS-based performance. You can find these two examples in 5G Toolbox. The latter one lets you compare performance of the AI scheme to existing codebook-based schemes as well as to perfect CSI estimation. As shown on this diagram, the coding-decoding impacts the selection of rank, which is the number of layers, modulation, and coding scheme, as well as pre-coding, also known as beamforming. In this next section, I want to highlight a few new capabilities in 5G Toolbox, which, although not directly related to Release 18 5G Advanced, are well worth being aware of. First off, Release 2024B introduces a new app called the Wireless Waveform Analyzer. With this app, you can interactively analyze a 5G waveform and display relevant characteristics such as spectrum, constellation, and EVM. You can load a waveform that was stored in a file, or you can directly load a waveform from an instrument such as a vector spectral analyzer. This app completes the flow for waveform generation and analysis. You can now both generate and analyze 5G waveforms interactively. So let's have a quick look at how this flow works. So in MATLAB, I select the 5G waveform app under the Apps tab. I can select one of the 5G options, full custom downlink or uplink configuration, or one of the waveforms defined by 3GPP test models, or downlink FRC, or uplink fixed reference channel. I'm going to pick a downlink FRC. You first select the frequency range, FR1 for sub 7 GHz or FR2 for millimeter wave. You then pick the modulation scheme and coding rate. Let's select 64 QAM. Then the subcarrier spacing and channel bandwidth. You can also add impairments. such as noise, phase or frequency offset, phase noise, or nonlinearities. And then you generate the waveform simply by clicking on the Generate button. So you can see the 100 MHz spectrum of the waveform at the top. At the bottom, the OFDM grid shows that most of the time frequency resources are occupied by data. You can now export this waveform to the MATLAB workspace or a file. In that case, you can select between different formats with or without metadata, or you can generate a MATLAB script that recreates the exact waveform or a simulating block. Here I export the waveform and associated configuration data to a file. Now let's start the 5G waveform analyzer. I can import the file I just created with the waveform generator. You can select the type of algorithm to apply. I am going to ask for IQ imbalance compensation. And now I analyze the waveform. So you can see the 100 MHz spectrum of the waveform, the PDSCH constellation at the bottom right, as well as the EVM display and information. You can visualize the EVM per slot or per symbol or over subcarriers. You can also see the estimated IQ imbalance. So let me get back to my slides. So we just used the wireless waveform generator, and we saw earlier that it now supports 5G advanced extensions with the ability to generate uplink waveforms with more than 4 layers. In addition to that, I want to mention 2 enhancements. You can easily pick an appropriate FRC for uplink waveform generation. This additional FRC selector picks the right FRCs given the characteristics you are looking for, and shows you additional characteristics of FRCs such as the number of layers or DMRS positions. You can also define characteristics of ESIB1 or System Information Block Type 1 directly in the waveform generator when enabling SIB1 transmission. A feature that has been requested by many customers is an example that shows how to measure performance of a 5G system in the presence of an interferer. This is the adjacent channel selectivity test. Release 2024B introduces such an example where the interferer level is set at a high level and the receiver attempts to filter out the interference in order not to affect the 5G waveform. The last new feature in release 2024B of 5G Toolbox that I want to mention is a brand new interactive visualization capability for CDL channels. If you have worked with this 3GPP channel model, you know that it has many parameters to configure the Doppler spread, power and delay profile, type of transmit and receive antenna arrays, and more. You can now get immediate feedback about the configuration of a CDL channel and see the OFDM channel response, raise and the departure and arrival angles, structure of the antenna arrays, all in the same window. This helps making sure that the CDL as configured corresponds to what you intended to do. I want to conclude this presentation with a view towards release 19 and beyond, including 6G. 3GPP is currently working on release 19 of the standard. I want to mention a few topics other than AI related that are being considered. The first one is an expansion of the number of channel state information reference signal ports from 32 to 128, something that will help get more accurate feedback data for ultra MIMO cases. Then the ability to have simultaneous transmission and reception. This is currently considered only in the GNB. The TX and RF waveforms would split the band. One of the main upsides is reduced latency because uplink transmission can happen more frequently. Another important topic for Release 19 and 6G is integrated sensing and communication. The ability to perform sensing at the same time as transmitting data requires channel models that include more detailed information about the location of the object to detect. For that reason, work is being performed on extending channel models with that kind of information for FR3. Two further enhancements are ambient IoT and ultra-low power mode that can be supported with devices with no battery or simple energy harvesting. Still about low power, a low power wake-up signal that would not require full control channel decoding by the UE. This could potentially save a lot of power if WUS detection could be done by a simple non-OFDM based detector. While there is no 6G standard yet, and there will not be one for a few more years, there is a lot of active research around topics that can be part of the next generation wireless standard. AI/ML will no doubt play an important role, be it applied to the physical layer or network level optimizations. In terms of frequency range, while sub-terahertz is still on the table, much excitement is coming from frequency range 3, wedged between frequency range 1 and 2. It seems to offer a great compromise between bandwidth and propagation characteristics. More exotic technologies, such as reconfigurable intelligent surfaces, are being proposed to overcome some of the challenges working at high bands. Also, it is very likely NTN will be highly integrated into 6G to facilitate communication for all. Finally, technologies like cell-free massive MIMO are certainly very interesting for improving efficiency with multiple non-collocated transmit and receive antenna arrays. With an eye on what is coming next, MathWorks has made a 6G exploration library available to enable some of this research to move forward without waiting for the 6G standard. In this library, you'll find capabilities to generate wider bandwidth waveforms, look at OTFS modulation, use the new waveforms in a link level simulation, and measure the impact of RF interference. You can study how reconfigurable intelligent surfaces can help overcome propagation hindrance, or help with sensing by scanning a room. You can investigate integrated sensing and communication, or cell-free MIMO. For more detail about MathWorks 6G capabilities, look for 6G in the list of on-demand webinars, or refer to the links at the end of this presentation. And this brings me closer to the conclusion of this presentation. We have seen some of the new features in Release 18 of the 5G standard, how 5G Toolbox supports this first version of 5G Advanced, including research around AI and ML. We took a quick tour of some of the other new features in Release 2024B of 5G Toolbox. And finally, looked toward the near future with Release 19 and the more distant one with 6G and the 6G Exploration Library. If you want to learn more about our 5G and 6G solution, visit our product page, sign up for our 5G training class, or watch some of the on-demand webinars available on our website. This concludes my presentation. I hope you heard something of interest today. The examples and capabilities mentioned in this presentation are current as of Release 2024B. Now, please post your questions via the chat window and we'll answer them as they come in.